The pull of the Earth. We are learning about acceleration due to gravity and mass and weight of an object. Activity. Throw a ball in upward direction and observe its motion. As the ball moves up, its speed goes on decreasing. It becomes zero at a highest point. The ball then falls with increasing speed. Take two balls of different masses, go to the top of a building, drop them simultaneously and observe what happens to the balls. The ball reaches the ground at the same time. Take two similar pages from your notebook. Crumple one paper and allow this and the other paper to fall on the ground simultaneously. What do you observe? The crumpled paper reaches the ground before the other one. Acceleration due to gravity. If an object is released from some height above the surface of the Earth, it falls freely on the Earth's surface. As the object falls, its velocity goes on increasing, which shows that the object moves with acceleration. This acceleration is called an acceleration due to gravity and is represented by the symbol g. Information. Scientist Galileo dropped two stones of different masses from the top of the Leaning Tower of Pisa and showed that they reached the ground at the same time. He inferred that the acceleration of a body falling freely towards the Earth does not depend on its mass. The uniform acceleration produced in a freely falling body due to the gravitational force of the Earth is called the acceleration due to gravity. Suppose an object of mass m is released from a distance r from the center of the Earth. Let m be the mass of the Earth, then using Newton's law of gravitation, F is equal to g into mm upon r square, where g is constant of gravitation. Acceleration is given by force upon mass. We can also write it in this way. F upon m is equal to 1 upon m into F upon 1. That is gmm upon mr square. We can also write it in this way. 1 upon m into gmm upon r square. Cancel the m on both the side. Now we get gm upon r square. This is called as acceleration due to gravity. From the above relation, acceleration depends on m, mass of the Earth, and height. It does not depend upon the mass of the falling object. Thus, acceleration due to gravity is same for all freely falling bodies. The value of g on the surface of the Earth. Here is some examples. Look it carefully. The acceleration due to gravity near the surface of the Earth can be calculated. The mass of the Earth is 6 into 10 raised to power 24 kg and its radius is 6.4 into 10 raised to power 6 m. M stands for meter. Substituting these values in the equation, we get g is equal to 6.67 into 10 raised to power minus 11 into 6 into 10 raised to power 24 into m upon 6.4 into 10 raised to power 6 whole square. So the acceleration due to gravity near the surface of the Earth is 9.8 meter per second square. The acceleration due to gravity is always directed vertically downwards, that is, towards the center of the Earth. If an object is thrown vertically upwards, its motion is in the opposite direction of gravity, and hence the acceleration is in opposite direction. That is, its motion is retarded by the acceleration due to gravity. Therefore, its velocity goes on decreasing and finally becomes zero at some height, after which the object begins to move vertically downwards under the effect of an acceleration due to gravity, due to which its velocity goes on increasing. Table below shows the variation in the value of g, that is gravitation, with altitude, depth due to the shape of the earth. So, let's look at the gravitation with altitude. The value of g decreases with altitude because the distance from the center of as we go to same height h above the surface of the earth, the value of g changes by 1 upon r plus h whole square. Where r is the radius of the earth, the value of g at different altitude is shown in the table. Now we will look at the gravitation with depth. If one goes deep inside the earth, the value of g decreases. However, the above formula for g is not applicable inside the surface of the earth. At the center of the earth, the value of g becomes 0. Thus, if we can conclude that the value of g is maximum on the surface of the earth, it decreases when we go above or below the surface of the earth. Now look at the gravitation due to the shape of the earth. We know that earth does not have the perfectly spherical shape. It is slightly flattened at the poles and bulges at the equator. Therefore, the radius of the earth at the poles is less than that at the equator. It is found from experiments that the value of g is different at different places on the surface of the earth, ranging from a maximum value of 9.83 meter per second square at the poles to the minimum value of 9.78 meter per second square at the equator. However, for all practical purposes, the average value of g at or near Earth's surface is assumed to be 9.8 meter per second square. Does the value of g change while going deep inside the earth? And why? The value of g changes while going deep inside the earth. It goes on decreasing as we go from the earth's surface toward the earth's center. We shall treat the earth as a sphere of uniform density. If we consider a particle of mass m at point P at a distance r minus d from the earth's surface, the gravitational force on the particle due to the earth is F is equal to gmm upon r minus d whole square, where m is the mass of the sphere of radius r minus d. This is because the outer spherical shell is not effective. In this case, the acceleration due to gravity is g is equal to gm into r minus d upon r cube, where m is the mass of the earth. Thus, g decreases as d increases. It is less than that at the earth's surface, gm upon r square. At the earth's center, d is equal to r, and therefore g is equal to 0. Why does an object released from the hand fall on the earth? When an object is held in the hand, the gravitational force acting on an object due to the earth is balanced by a person holding the object. When the object is released from the hand, it falls on the earth due to the earth's gravitational force. Does the value of g depends on mass of the falling body? And why? The value of g does not depend on the mass of the falling body. The reason is gravitational force on the body due to the earth is directly proportional to the mass of the body. Mass and weight of an object. activity. Take your book and go to a grocery shopkeeper. Ask him to find its weight for you by using his balance. Now take the same book to your laboratory and measure its weight on a spring balance. They may or may not be the same. It depends on the weight of the book and the quality of the two balanced use. The mass of an object is the quantity of matter contained in it. The SI unit of mass is kilogram, that is kg. It is a scalar quantity. The mass does not change from place to place. Mass can never be zero. If the mass becomes zero, the object will disappear. From the Newton's first law, we know that the mass is a measure of the inertia of the object. The greater the mass, more is the inertia. The beam balance at the shopkeeper can compare only mass. The formula for weight. W is equal to GMM upon R square, which is equal to mg. So, weight is equal to mg. The weight of a body is defined as the force with which the earth attracts it toward its center. If the mass of the body is m, the force of attraction of the earth or the weight W of the body is given by Newton's law of gravitation. So, W is equal to mg. Thus, weight will change from place to place as the value of g changes from place to place. It is maximum at poles and minimum at equator. Since weight, that is W, is directly proportional to g, the weight of the body will decreases when it is taken to higher altitudes such as mountains. It is maximum on the surface of the earth and zero at the center of the earth. Free fall. When a body falls towards the earth under the influence of the earth's gravity alone, its motion is called free fall. During the fall, the air opposes its motion by applying a force of friction and a force of buoyancy in the vertically upward direction. Thus, free fall in the true sense occurs only in vacuum. All bodies falls with the same acceleration g irrespective of their masses. As g is constant near the earth, all the equations for uniformly accelerated motion of objects become valid when acceleration a is replaced by g. The three equations of motion for freely falling bodies given as v is equal to u plus a into t changes to v is equal to u plus g into t. S is equal to ut plus 1 upon 2 at square changes to S is equal to u into t plus 1 upon 2 g into t square. Now v square is equal to u square plus 2as changes to v square is equal to u square plus 2gs, where u and v are the initial and final velocities, and s is the distance covered in time t. In applying these equations, we will take accelerations g to be always negative. During a free fall, will a heavier object accelerate more than a lighter one? No, the two objects will have the same acceleration.
In this topic, we have learnt about acceleration due to gravity, mass of an object, weight of an object.
That is all in this topic. Learning is fun, so keep learning.